So hello again. Tonight we're going to talk about an aspect of the lives of stars, how stars end their lives as either vampires or zombies. Yep, it's kind of a clickbaity title, but we'll get into the details of it. So rather than showing you astrophotography images of things, which might be in different spectra and false colored and such, I chose, if I'm going to talk about a simple principle like binary stars, and one's white or blue white, and the other one is reddish, I've got simple stars in a black background. So that lets you concentrate on just what we're talking about. So in general, we're going to be talking about the life cycle of stars and using terms like vampires and zombies, but it's not really Halloween. It's, something other than horror mythologies and literature. So it's about at the end of the life of a star, if you're part of a binary pairing, you could rob plasma from your sibling, and then that you could use that to re-energize yourself. And then your sibling could rob from you and maybe detonate itself if it gets enough of a shell on the outside of it. Or, both stars could be taken out. If you don't detonate one from the other, then this like vampire, zombie, vampire is likely to go back and forth for a very long period of time. And then we're going to discuss how does this play into globular star clusters and why what we originally thought about globular star clusters, we're now starting to get more information on them. And they're not quite what we thought they were. But at the end of the video, at the end of the presentation, and once I post the video to YouTube, there'll be a link to the Science Channel's YouTube video on how the universe works, and you can learn about their take on zombies and vampires and such. So this is a picture that I took from NASA JPL Night Sky Network. It shows the life cycle of stars, and you can see how sort of top left of center is our sun, a sun-like star, and it cycles around to the left, becomes a red giant, and then a planetary nebula, and then a white dwarf. And if you have a big blue star, it will become a red supergiant. And if it's energetic enough on its collapse, it'll go supernova, and it could form a neutron star or a black hole. But you can also see that there's a path from that supernova back to a star-forming nebula, and it all happens again. So you can see that there's a cycle for it. It's not just a line that branches out. It's actually circular. I'm not going to cover all of the thermonuclear physics of stellar formation and destruction, but I'll cover the kind of endpoints of the cycle. So when we talk about double stars, we can talk about two kinds of pairings. One is an optical double. This is where you see two stars from the Earth point of view, but they're not really associated gravitationally with one another. They're distant. They look close together, but since space is three-dimensional, there could be many, many light years, and they're not gravitationally affecting one another. That's an optical double. And then there's gravitationally bound pairings of stars. This is where one star is orbiting another star, like within a light year or so of it. So they're close, and they can actually have their orbital center between the two stars, and the two stars don't really orbit one another. They orbit each other. They're like turning together. And the other thing is, sometimes binary star systems aren't just binary. They're three stars, a large one, a medium size, and a small one. And they're all working together in a three-body problem. To just make a reference to the Netflix three-body problem. So we're only going to focus on two-star binary systems. Now, if the binaries are, if the orbital plane of the two binaries is pointed towards the Earth, like that, then we'll see one star go in front of the other star, periodically eclipsing it. But if the orbital plane is tilted 90 degrees, we'll actually see either two stars wobbling together, or we'll see one star orbiting another star. So all space is three-dimensional, and not everything is lined up for our entertainment. So things can be at different angles in space. But why is it that when you look at a double star, there's always one that's closer to being blue or white, and there's another one that's closer to being red or massive red. It's always this like endpoint differentiation between the two stars. In the case of our favorite out there called Albireo, that's Beta Cygnus, the nose of the swan. And when you look at it in space, it looks like one kind of grayish star, but just put a small telescope on it and you'll actually see a reddish star and a blue-white star. And there's actually 3 stars there because the reddish star that looks kind of gold in color is actually 2 stars that are orbiting one another very tightly, and their colors merge together, and that's how you get that gold color. If you have a binary pairing of stars and they were formed at roughly the same time, how come they're not the same type, the same color? And it's because differentiation, just a small variance that allows one of the stars to get more massive quickly than the other star, it will actually rob remaining gas and dust because its gravity is greater than its sibling. And if it does that enough and it gets big enough to make fusion happen, it will switch on before its sibling does. And the switching on produces enough force to blow away the remaining gas and dust, and its sibling will never get any larger. So that's why you always have, like in a pairing of binary stars, one is going to be the bigger one and the other one's going to be the smaller one. And it also explains why they have different lifespans, because a blue-white star may burn hotter, but it's shorter lived than a orange or red dwarf star, which is going to last for even millions to a few billion years longer. So when we first started looking at stars, I don't mean we as in me, I mean people on this planet as curious astronomers, they would look at things like Albireo, naked eye, and go, that's an interesting star. It's fairly bright. It's around the 5th brightest star in the northern hemisphere. So it's fairly bright. But then when they put telescopes on it, they went, oh, it's 2 stars, 2 for the price of 1. And then as we got better telescopes, we went, oh, wait a minute, one of those 2 is actually 2 by itself. So it's like double your pleasure, double your fun. So you get a double within a double. And we've got others out there. We've got clusters, the double-double. And we've got stars that are double-doubles. As you get more resolution, larger telescopes, better imaging, you're not using like emulsions on glass plates. You're using high-resolution digital cameras. You start to find that what you thought something was isn't. It's something different. So when we were looking at globular clusters early on, looks like there's maybe a few hundred stars there. And they all look to be like white because we didn't have very good color rendition in our, emulsion coated plates. So globular clusters were these things that hung out on the edge of our galaxy, and they're very old white stars. And there's hundreds of them in there. If the stars were really all the same, then the stars would be equally all the same type. But whenever you listen to people talking about historical astronomy, they'll say that the stars in a cluster or in a globular cluster were mostly or predominantly white, as opposed to, well, you got kind of a mix of some blue, some red, and the really old ones are the white ones. They should be, if they were really uniform, they should have been saying equally as opposed to mostly or predominantly, but sometimes people get stuck on the way they've always talked about it, and that's not the case anymore. So globular clusters, the largest globular cluster in our galaxy is Omega Centauri, and this was, that one's more than hundreds. That might even be thousands of stars. And now that we have better imaging capability, bigger telescopes, we realize that they're not all the same color. They're not all white. I'm seeing reds and blues and lots of whites, but there's a lot more stars there. So we said, well, those aren't normal. These are oddballs. These are things that used to be entire small galaxies all to themselves, and gravitationally the Milky Way just captured it. It was flying along, and we just sucked it up and made it our own. That's why they hang out on the edge of our galaxy. Yeah, you might have believed that stuff back when we were doing visual observations or hand drawing things, but now that we're moving from monochromatic into color and higher resolution, we know more about this stuff, and some of those things are no longer what we think they were. So the current understanding is Omega Centauri, largest globular cluster in our galaxy, has over 10 million stars in it, and it's about 100 light years across. So the density of stars per light year is pretty tightly packed. And the question comes down to why so many stars are clustering in such a small amount of space. Usually it's because there's a large gravitational source, but unfortunately we don't have good enough instrumentation to be able to see to the core of globular clusters. The stars just get too dense for our resolution, but we might find out that maybe there's a black hole in the center of these clusters, and that's what glues them all together and why they hang out on the edge of the galaxy, until we found out that, globular cluster M4 in the constellation Scorpius, that's not, many tens of thousands of light years away from us on the edge of the galaxy. That's only about 5.5 thousand light years away from us, away from the center of the galaxy. So you have a globular cluster that's not hanging out on the edge of the galaxy. But I thought we captured all of these. It can't really be a story of being captured if it's on the inside of the galaxy. So we're starting to learn more and more things the more we look. They gave a name to those blues because the bright blues in a globular cluster, there aren't that many of them. So they don't know why they're there. So somehow they think they were captured by the cluster. So they've identified them as stragglers. Like a star was just roaming around and got caught up in this globular cluster. And now we know maybe it was one of those other stars that got transformed. So we know that blue-white or white star, active white stars are hotter and brighter, and they live for only maybe millions of years. But we know that the colder, redder stars, or white dwarfs at the end of their lifespan, they could be potentially billions of years. So if all of these stars formed at roughly the same time point, why is their lifespan so different? What's that got to do with the structure of the cluster? And it's because prior to us studying clusters in more detail, we used to think of stars as standalone. Here's the life cycle of a star. It's one of these or it's one of those. We didn't think of it as, if it's a binary pair, the stars are very close to one another and they can affect one another. And by affecting one another, maybe it's that a cluster is nothing more than a large collection of binary stars, and they're all working off of each other as siblings, but the cluster itself is just a collection of these siblings. And that could be why we're seeing this mix. So there are remaining questions about globular clusters. Why so many of them in a cluster? And why such high density of the binaries as you get towards the center of the cluster? Is there a massive gravitational source at the center, like a black hole, that we can't see visually? And why is it that we have so many clusters in our galaxy? Maybe there's a recurring phenomenon. It's not this accidental capture stuff. And why are they mostly on the outskirts of the galaxy? Yes, M4 is much closer to us than most of the other globular clusters, but why is it that they tend to hang out towards the edge? Could it be competition, as in if they got any closer, the black hole at the center of the galaxy might pull them apart, and then they would just be spread into the disk of the galaxy. But if they can cluster on the outside, then whatever's in the core of that cluster will actually be holding them together more tightly, and gravitationally it will hold on the outside of the galaxy as a clump. But here's the ones I came up with, as I don't see anybody talking about these. So we know that we've got these red stars, blue stars, and white dwarfs how come no other kinds of or no other colors of stars in clusters? How come there's no like, G2 type Earth, Sun kind of yellow stars, which is actually green, or orange stars? Orange stars are kind of like red stars. They're just a little bigger and a little hotter. Why is it things are only at the extremes? How come we don't have a complete spread of different kinds of binaries? They're always like at the ends. So we'll first cover the vampires. So if you have two stars in a binary pairing, physical binary, they're gravitationally intertwined with one another, and one of them is towards the end of its lifespan. It's kind of about to go from like a mid-star to a white dwarf, but it's paired with another star that's also towards the end of its life, and it's redder. It's the bigger, like it's got internal pressures increasing the size of the star until it becomes like a red supergiant. But as it does that, it's going to push out plasma beyond its ability to gravitationally keep it in. That's why it just keeps growing. But it'll grow out far enough to the point where the white dwarf will now start to suck in that loosely held plasma from the red supergiant, and it will spiral into the white dwarf. This is like adding more fuel to a star that has run out of fuel. So the white dwarf takes in this extra plasma and regenerates. It's a vampire that's sucked in plasma, and now it can spring new life. So you have what was originally a white dwarf that, without a massive explosion, once again becomes a blue-white star, a hotter star, because it got a fuel charge from its sibling. Now, its sibling didn't really like that, because when you have a star that's already losing its gravitational force and starting to swell out, that red supergiant is going to accelerate its demise. And that's when it is referred to as a cataclysmic variable. So they've already got names for these from how stars behave. They just didn't tie it into the life cycle intertwining of the two stars in the binary. So the white dwarf becomes the vampire of the two. But then as the red supergiant has lost more of its outer shell, that means its end of life event, which is usually a collapse, can take place sooner. So the blue star gets switched on to be blue or blue-white, and then the original supergiant red collapses down. And when it collapses down, it becomes a white dwarf, just like its sibling used to be. So they swap roles, and now the vampire is attacked by its sibling, and the white dwarf result of the red supergiant wants to detonate. If it gets enough energy and it collapses down fast enough, it can actually detonate. And when it detonates, it can take out its sibling. But these are cycles that might take millions to billions of years to go back and forth. And every time it cycles, it reduces the total amount of energy, because when that red supergiant was bloating out, or when the white dwarf was detonating, it pushes out material. And the more material it pushes out cycle after cycle, the less likely that that detonation is going to destroy both stars. So now what we have is diminishing returns. So if it cycles, vampire, zombie, zombie, vampire, vampire, zombie, zombie, vampire, and it keeps diminishing the total amount of energy, the total amount of plasma available for cycling by the two stars, eventually what you'll get is the one that became a white dwarf no longer has the material coming from its sibling to feed it anymore, and the one that was the red supergiant no longer has enough left over to detonate, so it just collapses then and becomes a white dwarf. So what you had originally as two different kinds of stars becomes predominantly just white dwarfs. And this is what we're seeing. In the globular clusters that are the oldest ones, the ones on the outskirts of the galaxy, the ones that are the oldest ones that we can determine, all seem to be white dwarf stars. And now that we can see things in infrared and ultraviolet and radio and as well as visual, they're white dwarfs. Diminishing return results in what was once two different kinds of stars cycling back and forth as a binary pair in a large collection that was a globular cluster is now smaller, and the ones that blew up are obviously gone, so there's a little head count loss, but the ones that remained are all cycling down to becoming white dwarfs. And if you want to know, this particular example is M4 in our galaxy. If early on in the cycling, you have just enough plasma transferring between the two of them that the red supergiant gets enough accretion on the outside of it, it now has enough energy to fuse carbon. And when it has that much energy, when it detonates, instead of it being a nova, it becomes a type 1a supernova. And if that's the case, we should be able to see those from Earth. Well, as it turns out, this doesn't happen that often, because if all cycling binaries eventually led to a type 1a supernova, and something with as many binary pairings as a globular cluster, there might be millions of stars, we should be seeing type 1a supernovas all the time out of these globulars that are multiple colors. But we're not. They're rare. So that says the detonation that destroys both stars or stops the cycling is a really rare event. And if you've ever heard of the butterfly effect, it's something small can affect something large. And if you have enough of a lot of small things, it can affect large things. So there's a butterfly effect that if you have a globular cluster and you have millions of stars that are all cycling in pairs, and remember I said that one star switched on a little earlier than its sibling. Well, if you multiply that out over all of the binary pairings of the cluster, you now have an overall effect taking place within the cluster where no binary pairings are in sync with other binary pairings, because if they were all in sync with one another, then when the switchover from like red and blue and white was occurring, globular clusters would look like Christmas tree lights. You'd see massive shifts like all red to all blue or all white to all red, and you don't. They're very individually switching. So that's the butterfly effect that from cluster to cluster, nothing is in sync. We're not seeing this massive color transition. We're seeing individual color transitions. So in conclusion, if you understand the subtle things and you get increasing awareness of them, it can empower your ability to know what's really going on as opposed to what you originally thought going on. The one I like to remember is I have a science book on my shelf in my library area that discusses the Great Andromeda Nebula back in the 1920s. And now we know it as, no, it's not a nebula, it's a galaxy. Well, in my lifetime, it was Albireo, it's a double star, but now it's known as a triple star. So don't get too locked into things being what you think they are. Keep studying them. You may find out that they're different. Like Omega Centauri, back when we were just looking at things visually, was thought to be a single star. It was thought to be a star, a really bright one, but a star, and therefore didn't fall out as an asteroid or a comet. So our understanding of globular star clusters has changed in my lifetime, as the saying goes. And as the imaging and sensing technology improves, we're finding out more detail, but we have yet to see what's in the core of a globular cluster holding it all together. Simply our knowing that they're pairings, and there's a lot more pairings of stars in the cluster, has brought to life the fact that stars don't exist individually. They might exist in pairings, and when they exist in pairings, things can spawn off of one another, and it can cycle back around. And some of these may be repeating and renewing themselves, and it may last for billions of years. There's things that need to be understood about binary stars and star clusters. And until we know them, you'll never know how much you didn't know until you know what you didn't know. My favorite. But in the case of science, if you think something is something and you want to hang on to that, like, I know this to be true. Well, okay, then you knew it to be true. But don't let that stop you from keep observing it in more and more detail with better and better instruments. You may find out that's what we used to think, and now we think something different. So don't be dogmatic about scientific precepts, because if you keep observing, keep looking, keep improving, you may find that you have some answers from some of those questions, or you might actually come up with more questions now that you have data. And then we've got some links. I started off with the Science Channel YouTube video on stars, vampires, and zombies. And then Alberio being a triple star system. And the way that we know how old these clusters of white dwarfs are is by their metallicity. Helium and hydrogen are metals in the periodic table of elements. And when you run out of helium and hydrogen, it means the metallicity of your star, when you look at it spectroscopically, says there isn't a lot of helium and hydrogen left in that white dwarf star. So it's not going to, spring to life again all on its own anytime soon. But when it draws from its sibling, it can switch back on. And you can do that as many times as you can find plasma for it. And then, of course, for people that want to make reference to it, Alberio, it's a three-body problem. Okay.
That's funny.
No mathematical formulas. Questions, yes, but no significant postulations. I was drawing upon historical scientific fact and current understandings. So, comments, questions?
No, it's funny. That's cool.
Well, yeah, I wanted to ask you. You mentioned a triple star.
Yes.
Wouldn't there be other situations where multiple stars would be reacting with each other?
Well,
oh yeah,
they have to be close enough together.
Yeah.
And remember me saying that if you have a nebula, a gas and dust cloud, and gravity and electrostatic attraction are starting to pull some of the gas and dust together, it will form like denser and denser material. And once it gets to a certain density, you might get a brown dwarf star, like a failed star, like something bigger than Jupiter that has enough gravitational compression to get hotter and hotter and hotter. And the amount of stuff that it pulled in, if it grew more rapidly than another star that was born at the same time orbiting with it, then one is going to blow away when it switches on all the excess gas and dust. And your little brother is going to stay your little brother forever, because you never gave it a chance to get all it needs to be the same height and weight as you. So yeah,
the physics is going to be that there can't be more than really two stars.
No, there can be. In fact, I remember having read about a quaternary star system, a 4-star system, but that would say none of the stars got to be relatively big at the same time, because whatever gas and dust is left over, maybe they formed into terrestrial planets, but we won't know until we see one. There are people that think that our sun star system is actually a binary, and the other star is just way far away, and it takes a long time for it to come back around, many hundreds of millions of years. And that's why we have in the historical record, every several 100,000 years, there's a disruption of the Oort cloud and the Kuiper belt, and we get more comets coming in. But we have no proof of that. If it was another star paired with our sun, the farthest away it's going to be is a few light years. And we can already detect stars at that distance, like Barnard star, that moves tangentially to our movement through the galaxy. So we can see that. but we can see in infrared and ultraviolet and visual, and we have much better telescopes and much better imaging. So we've done surveys like the Gaia survey that looked at all the stars, and that's how we know that there's over 100 billion stars in our galaxy, not just a billion, because we can see more. And as we can see more, we're not seeing another star that would be in our neighborhood that is either moving away, like it's part of the orbit of our sun, moving away or heading back towards us. We see one star that's moving tangentially across our view. Anything else?
Since there are so many stars, it seems that there's bound to be situations that we could observe, such as on edge or.
Oh yeah. Well, we do that. We do that with galaxies already.
Yeah.
There is the Pinwheel Galaxy, the Sombrero Galaxy, Andromeda. Andromeda is like a little bit tilted towards us. Sombrero is almost edge on, and the pinwheel's like this.
Yeah.
So we already know that space is three-dimensional, and not everything is properly positioned for our entertainment viewing.
Yeah.
Different things at different angles.
Yeah.
We know that there are planets. We know that there are planets in our solar system that don't all exist within the plane of the solar system, like Pluto. Pluto is a little eh. And we know that which is Uranus. Uranus is flipped on its side. So much like space is three-dimensional and big, things aren't always aligned the way you would expect them to, and they're not always aligned the same way. So you've got to take that into account when you're classifying things.
And that's good for observers because they can find these unusual things. And
well, we have solar and lunar eclipses not every month, not every 28 days, because the orbit of the moon is tilted about 5 degrees to the equator of the Earth. If it was spot on at the equator, then only certain parts of the planet would get solar and lunar eclipses, but they would get them every 28 days. But we don't, because it's slightly tilted, so the shadow of the moon made by the sun misses the Earth, or it winds up in the Atlantic or Pacific Ocean out in the middle of nowhere, or in Siberia out in the middle of nowhere, or the Antarctic out in the middle of nowhere. Things go bump in the night, and ships pass in the night, and yeah, all those things that we do believe in, but space has to be given the same latitude.
I know before I even thought about binary stars, I was taught that the stars at night are big and bright in Texas.
But only deep in the heart of Texas.
Yeah.
Yeah.
That's all I knew about them.
Yeah. Okay. Anything else? We can continue talking afterwards, but I'll stop recording. Hearing nothing.